chi-squared tests are one of the most important tests that you can do in statistics. So they're used for categorical data for testing associations. So this means when you have data which is not measurements but instead counts, which can either be ordinal or nominal. So the data can't be summarized by means or medians, and you can only tabulate it. So what you want to know is, are the counts in your sample, do they agree or disagree with your hypothesis? So what you usually assume is that you have equal probability for each of the rows of your table. So contingency tables are a table of frequencies. You can have measured frequencies and compare this to a null hypothesis, or you can look at two different, a treated and untreated row of data, and then see if the probabilities of falling in the categories are the same in the different rows. Now, often you get these contingency tables, you see them in papers or you read them in articles, and they're summaries of the data. The raw data itself should look very different. So it should contain a row for each of the individuals that you've collected, and then their specification as to which category they fall into. Now, treatments have to be considered in a very general way when you're thinking about categorical data. It means your categorical data has been collected in two dimensions. So you have one dimension which you think is affecting the other. So we're going to come on to the example of snails. So one dimension is their environment, and you think it affects their colours, their colour schemes and the patterning of their shells. So you want to know if the frequencies and therefore the probabilities are different between the two different groups. The usual way of formulating is each one of the rows corresponds to a different environment, to a different treatment. I mean, the treatment could even be gender, so you can look for gender differences in preferences. So rows are the treatments, the independent variable, and columns are the outcome, the dependent variable. To test whether there's a difference between the two, you carry out what's called a chi-squared test of association. Now you need more than 5 expected counts in each shell. So if I was asking a survey between men and women, and it had 5 different possible answers, then that particular survey, for each of the groups, for men and for women, I need to ask 25 people, so that on average I get 5 of each of the different answers. So let's look at an example. So this is the shells example that I talked about, Sepia nemoralis, a common snail that comes in colours which are banded yellow, non-banded yellow, banded pink, non-banded pink. The biologists in this particular case were trying to see if there's a difference between coastal and hedgerow in the patterning and coloration of the snail's shells. If you look here, there are 50 snails were collected in the coastal region, 55 were collected from the hedgerow, and of the different colour schemes you've got 27, 27, 24 and 27. So you've got about equal numbers of each of the colour types and from each of the two different locations. Total number of snails is 105. What you can do is figure out the frequencies. So what's the probability of being coastal? It's 50 out of 105. What's the probability of being banded yellow? That's 27 out of 105. So the probability of being coastal and banded yellow is 50 over 105 multiplied by 27 over 105. So that tells you the probability of being in that first square of the table, the coastal banded yellow square. Now if I multiply that by 105, that tells me the expected number of snails I should have observed if that probability is true. So that's what SPSS is doing. It sums up the rows and columns to get the marginal totals, calculates the probabilities of the rows and columns, which are called marginal probabilities, predicts the number for each of the different cells, and then calculates the chi-squared statistic. And the chi-squared statistic is dependent on the observed minus the expected divided by the expected. You then have an issue of degrees of freedom, which is the number of rows minus 1 multiplied by the number of columns minus 1. So within SPSS, using the Sapir and Nemorales data, you have habitat and colour. So this is what it looks like in variable view. You notice that in values you've got 0 for coastal, 1 for hedgerow, and you've got the different colours. 1 is yellow banded, 2 yellow non-banded, 3 pink banded, 4 pink non-banded. They're all nominal because they don't have any particular order or preference, and they're definitely not scalar because they're all categories. But this is what the data looks like as actual raw data. So for each one of the snails you collected, you put down what its habitat was and what colour it was. So that means the first snail was from the 0 habitat, so the 0 habitat is coastal and had colour banded yellow banded. Right, so you've got 10 of those, then from column row 11 onwards you've got them yellow non-banded. So in total this data set will have 105 rows. Now how do you do the analysis in SPSS? Go to descriptive statistics as usual. Now in this case we want to do the cross tabulation, so you can see from the menu that cross tabs is the 4th menu down, so you need to select cross tabs. Once you've selected cross tabs, you need to put in the rows and the columns. Now habitat is the independent variable, so it's the treatment. You think that different habitats are going to change the number of snails of each of the different colours. So the colours and patterning of the snails is the columns, and that's the dependent variable. Once you've done that, you can see on the right there's a set of buttons. So there's exact, meaning exact test. We'll skip that one. Then there's a thing that says statistics, then there's cells and format. Cells and format allow you to turn things into percentages to make the table easier to understand, potentially. But what we're interested in here is carrying out a chi-squared test, so you want to click on statistics. When you click on statistics for chi-squared, is the first of the options. There are other options that you can do. So for example, if you were doing the 2 rows were not independent of each other, like they are in this case, if the 2 were dependent on each other, so you were using a method for diagnosis which has a yes or no answer, as in found to be ill, found to not to be ill, and you're comparing 2 different methods, then the samples, the people involved with that, are exactly the same samples for both of the different tests. So then they become dependent. So you wouldn't use a chi-squared, you'd use Cochrane's and Mansell-Hintzell statistics. So you'd tick another button. In this case, you just want to pick on the chi-squared. You see on the right hand side there's a thing that says kappa, risk and McNemar's. McNemar's is another test for doing dependence, like Cochrane's and Mansell-Hintzell statistics. If you want to calculate the odds ratio, you can click on the risk button, but let's ignore that for now. Just click on the chi-squared. So it gets the raw data. It sums it up and says there's 10 yellow banded, 19 yellow non-banded, 5 pink banded, 16 pink non-banded, total of 50. So that's reproducing the data table that I expect it to do. Then goes down and it calculates the Pearson's chi-squared. So the chi-squared statistic has a value of 15.185, has 3 degrees of freedom, and it has a p-value, so there's the asymptotic significance, is that what that abbreviation stands for, of 0.002. That's below 0.05, so there's a significant difference in the distribution of colours and patterns between coastal and hedgerow. A more modern method than chi-squared is likelihood ratios. I'm not going to go into describing those other than to say they're a new improved method. You can use them if you want to, but again you have the statistic and you have its p-value, and the p-value is 0.001, which is definitely less than 0.05, so it is significant difference using likelihood ratio as well. There's a special case for calculating the the chi-squared statistic if you've only got 2 rows and 2 columns. So that is called the Yates correction. If you do SPSS, it will give you an extra column of the chi-squared with a little footnote to say this is the Yates corrected value. So instead of using the regular chi-squared formula, which is the sum of the observed minus the expected squared over the expected, you do the modulus, so observed minus expected, then ignore the sign, minus 0.5, then square that, then divide by the expected. This gives a slight correction to remove bias in the case of a table which is 2 by 2, where you've only got 1 degree of freedom. Otherwise, there's a possibility that you might get a biased result.